Good morning, good afternoon, and good evening. Thank you for joining Android Day 2023 on Google Open Source Live. If you haven't attended Open Source Live before, it's a monthly web series where each month we explore a different topic within open source. Today, of course, is all about Android. My name is Sandeep Patil. I'm a principal engineer in Google. I work on Android's system software. Today, I'm joined by my co host, Todd Chose, to take this Android journey with you all.
Thank you, Sandeep. Hello, everyone. My name is Todd Chose, and I'm a software engineer here at Google, leading our Android kernel work. I look forward to co-hosting today's event, showcasing some exciting virtualization features that our team delivered in Android 13. Sandeep, please tell us what's in store for today.
Our team has some really interesting topics today. If you're looking forward to learn more about Android and its internals, you're in the right place. We'll kick it off with an exciting talk from Matthias Manik, who will walk us through the Android Linux kernel in AOSP. Later, we will hear from Stephen Moreland and Will Deacon to discuss some key components of Android virtualization framework. Stephen will discuss CrossVM, the virtual machine monitor, and Will talks about protected KVM, our extension to Linux's KVM hypervisor. Finally, we will hear from Alistair Delva, who will talk about Cuttlefish, the virtual device that powers Android's continuous integration and development at a very large scale.
Don't forget to put your questions in the live Q&A forum below the live stream window. Speakers are ready to answer your questions live. If you are viewing in full screen, you'll need to exit full screen to see the live Q&A forum. Our sessions have been pre-recorded to allow for accurate transcripts and so that speakers can focus on answering your questions live. Once we are done, don't forget to join us at the after party. You'll see a button to join in the event page at the end of the last session. Oh, and last but not least, use the hashtag GoogleOSLive to share your experience on social media.
With that, I will hand it over to Matthias Manik for the first session.
Hello, I'm Matthias from Google. I'm a software engineer in the Android systems team here in London. 4 years ago, I joined, and since then, I focused on the GKI process and how we can support it with tooling. But more to all of that a little later. This talk should give a fundamental understanding of how Android is using the Linux kernel as base for the Android operating system, how kernels were and are developed in AOSP and across the partner ecosystem. I will talk about the generic kernel image, GKI, its motivation, and a little bit about its design principles. First of all, I would like to introduce you to the Android Common Kernels, ACK, as it's commonly abbreviated. The ACK are based on the Linux kernel, and hence all Android kernel development happens as a fork of the upstream kernel. In other words, downstream of the kernel.org releases. Those releases include the ones done by Linus Torvalds, release candidates, as well as full releases. Additionally, and relevant for the actual binaries on devices, we ingest long-term support, LTS, kernels. The difference between ACK and the upstream kernel is just what is needed to run an actual Android stack. A bit of build system integration, binder, scheduler, and other areas of the kernel. In total, a bit more than 100 patches, which sounds a lot, but if you look at them, there are actually not so many patches anymore. There used to be many more that were out of 3 differences. All development happens in public only, in AOSP. That includes the merges, as well as any patches contributed from partners or the community. The result forms the base for every Android device, and we are talking about over 3 billion active devices right now. As much as we love contributions, we like them to go upstream first. We strongly encourage and support the community and partners to upstream patches into Linux mainline first. That way, they are aligned with upstream, they are maintained as part of upstream development, they can receive tree-wide improvements, and automatically, obviously, they are part of every Android kernel tree. We accept contributions for Android-specific features, like, for example, the mentioned build system integrations. We also accept backports for upstream features, if reasonable, according to our contribution guidelines. Again, all development happens in public. Even the build and test infrastructure is publicly accessible. There is no secret source for building or developing kernels. And everything is publicly documented on source.android.com. As a result, in 2022, the ACK, the Kernel Common Project, was the AOSP project with the most non-Googler contributions. This slide gives a simplified overview of how code flows in AOSP from upstream to release branches downstream. The starting point is the upstream Linux kernel master tree, also referred to as mainline Linux. Every release candidate and release gets merged into Android mainline, usually within days. Android mainline can run on devices like Pixel 6 for development purposes, and we try to keep it that way. Every time we merge from upstream, every time we touch Android mainline, we are actually running on real hardware like the Pixel 6 for verification. Whenever there's a yearly LTS release, usually the last one in the year, we also create corresponding Android version development branches. For example, when 5.10 was created and that release merged into Android mainline, we forked Android 12 5.10 away. Similarly with 5.15, which forked into Android 13 5.15. After that, those branches receive timely merges from the LTS release that is cut at the same time. Timely meaning we expect an LTS release of every branch to happen roughly once a week, and latest a couple of days later we actually have it incorporated in our branches. Eventually, after stabilization and possibly some more feature development specific for that Android version, a release branch is cut. That branch is used to build the binary that ends up on every device. Some years ago, this model was rather a recommendation, and we faced heavy kernel fragmentation in the field. Every device forked off, say Android 13 5.15, at some point into a completely own and separate kernel tree. This made it hard to get kernel updates and fixes, like security fixes, into the field. Kernels appearing on new devices were already years old. Around 2018-2019, we started addressing this problem with the GKI program. Having addressed Android platform fragmentation with Project Treble in Android 8 by separating vendor bits from core Android bits, we try to apply a similar philosophy to the kernel development. By separating again vendor bits from core Android bits or from core kernel bits. That way, we can make the kernel part of the Android platform that is common to all devices with all the development and releasing benefits. We can address fragmentation, updatability, and eventually we can release fixes, including security fixes, at a much higher pace and scale. Lastly, by getting devices on newest kernels, we encourage our upstream first philosophy in development and innovation. GKI kernels contain facilities to allow the partner ecosystem innovation while protecting their IP, while still using a common kernel code base for every device. Unreleased hardware booting with open source kernel used to be fascinating and mind-blowing, but nowadays it's actually the default that happens all the time. The architecture of GKI is fairly simple. The generic kernel and the GKI modules are originating from ACK from a single source, and vendors develop against the API of the GKI. The APIs to the Android platform, the kernel userland API, are kept stable. That is a Linux principle. The APIs and the APIs to modules, on the other hand side, provided by vendors are kept stable. The KMI, the kernel module interface. That is not an upstream principle. It is very much breaking all the time. But an Android-specific guarantee we give for the GKI kernels. There is quite sophisticated tooling to ensure the API stability of those interfaces. I will say some words more for that later. Those guarantees eventually allow independent kernel development of GKI and vendor parts. In theory, we could even update the kernel and the modules independently. Though that's actually not something that happens in practice, as everything comes bundled from the vendor. Now, let me give you a little bit of an overview of how we got where we are actually right now. In 2016 and earlier, we can consider everything as unregulated, heavily fragmented. 2017 was when some restrictions were introduced, like the minimum kernel LTS versions. So vendors had to use a minimum LTS version for the kernels that they use. Android Pie marks the first time vendors are supposed to have their kernels downstream of ACK, basically forking from the Android common kernel. And as mentioned in 2019, we started the GKI work. As a first milestone of that, in Android 11, we released GKI 1.0. Released devices needed to be compliant with GKI. That means devices needed to be able to swap out the release kernel against the ACK GKI kernel under test. That way, partners could do all the modifications in the device kernel as long as the kernel was compatible. 2021 marks the year that devices started shipping with Google built binaries. Again, all publicly built on our public continuous integration system. One of those devices was the Pixel 6. At the release, the Pixel 6 kernel came with Android 12 5.10. What was remarkable was that 5.10 was at that time the newest LTS kernel released. It was less than a year ago. In 2022, we can see that the GKI model is now largely adopted in the partner ecosystem, and branches predating GKI are getting deprecated. In 2023 and Android 14, you can see us already working on AOSP, on improving developer experience, the partner integration even more, and our tooling. This chart gives an overview of the adoption of kernel branches on released devices in the field. The absolute scale is not really of relevance, but the relative scale is. As you can see, along the process of developing GKI, kernels reach the field with decreasing delay. As mentioned, 5.10 in the field was available less than a year after the upstream release. As we know, newer kernels are usually better supported and also receive updates longer. What also sticks out in this chart is obviously 5.10, with the strongest early adoption rates. But another interesting fact to notice here is the adoption of 5.4. Android 12 could be launched with either 5.4 or 5.10, and partners dominantly picked the younger kernel, leaving 5.4 behind. Finally, let me give you a brief overview of how GKI is developed. In order to achieve the GKI goals, such as updatability and innovation, and to support the single source, single binary approach, some technologies needed to be developed. First of all, we needed to ensure a hermetic and deterministic build. Without that, any guarantees about binary stability are just unreasonable. But more about that in a second. Next, we needed to ensure we are able to verify our GKI stabilities in terms of ABI stability for the KMI, but also in terms of testing. By defragmenting the kernel sources, the introduction of general large-scale testing really made a difference. Lastly, a lot of energy went into creating interfaces for vendors that allow the usage of the single kernel for everybody, while at the same time we offer the flexibility to use the kernel for a multitude of different devices powering Android. Hermetic builds are essential not only for the stability of the GKI kernel and its ABI, but furthermore, a consistently and well-defined build system allows adoption in the community and partner ecosystem. Consider the various different system setups on development and infrastructure machines and how they possibly influence the outcome of the build result. As a result, when building GKI kernels for Android, every single input is declared. Sources, tools, everything is accounted for. A fixed configuration is part of the build definition. Any changes to it are subject to scrutiny and review and testing. We use Bazel to orchestrate the kernel builds and sandbox environments to isolate from the host. It should not matter when and where a build is made to yield the same result. And as a matter of fact, we hardly see any bugs that are that we cannot reproduce in our lab. The ABI, or KMI, can change due to various reasons. There could be actually breaking source code changes, configuration changes, or tooling changes. Either of them can be very subtle. In order to ensure the ABI stability guarantees of KMI, sophisticated tooling is in place. We do static analysis of the final binary. Based on extracted ELF and dwarf information, we compare the ABI representation of a candidate kernel with a proposed patch against the representation of a base representation of a committed kernel. We use fairly complicated type graph comparisons in order to identify differences that sometimes are subtly introduced. We are developing a tool for general ABI analysis, not only for kernels, called SDG, Symbol Type Graph, for this purpose. And of course, the sources are available in AOSP. Since GKI was a paradigm shift, not only for Android, but equally for vendors, in collaboration with partners, we developed facilities to allow a transition into the GKI model. Arguably, the most effective one is the introduction of vendor hooks. They are a callback mechanism via ftrace that allows almost arbitrary hooking into core kernel code via loadable modules. As a result, partners contribute locations where hooking is beneficial for them and gaining the flexibility needed. As a side effect, we see discussions spinning off vendor hook contributions that sometimes lead to upstream contributions, making their vendor hook obsolete in the long run. We require partners to contribute their use cases of the KMI in terms of symbol lists that describe what symbols their modules require from the core kernel. That way, we gain visibility, what areas of the kernels are in use, and we also are able to restrict the ABI that we have to keep stable to just the bits that are used on actual devices. Over time, we naturally created feedback channels with partners, and what used to be a Google-only development project is now a community project with partners contributing not only to the kernel itself, but also to the tooling, like for example our new driver development kit that we are releasing for Android 14. Thank you very much for your attention. I hope that was an interesting talk and gave some insights into how the Linux kernel is used within Android, powering several billions of devices. Thank you very much. Goodbye.
Thanks, Matthias. I really enjoyed the multi-year journey to get to a unified Linux kernel for Android. GKI exemplifies how a diverse community of developers in Android and Linux came together in open source to deliver a common goal. Next, we'll hear from Stephen Moreland, who will be sharing more about CrossVM. Take it away, Stephen.
Hi, my name's Stephen Moreland, and I'm a staff software engineer at Google. And one of the projects I work in is called CrossVM. And today I'm going to be talking about how to fold software onto the edge of a fractal. So I'm going to be talking about how we use CrossVM in Android, how we bring in such a large code base into Android, and how that affects the architecture of Android. First, what is CrossVM? CrossVM is a virtual machine manager developed by the Chrome OS team, and it's written in Rust. It has an architecture that looks like this on the right. Basically, you give a device image, files, some parameters, some devices that you want to set up to CrossVM, and it talks to the Linux kernel or some other kernel or some other hypervisor manager, and it'll spawn a VM, and then it allows you to talk to that VM. And so it manages the lifecycle of VM, and it uses shared memory to pass information to the VM. It sets up all of the devices that allow the VM to operate, and it also supports a sandboxing mode, which splits CrossVM into multiple processes so that it takes advantage of process isolation to provide a more secure VM. And this is used for Chrome OS in order to run Android in Chrome OS, and we've also used it for Cuttlefish on Android for several years now, and that's a virtual machine, a virtual Android device, and it runs on CrossVM, and we can use it to test our code in Android. I'm going to be talking about why CrossVM first off, and then I'm going to be talking about some of the difficulties with integrating such a large code base into Android. And then finally, I'm going to talk about how we've adjusted the architecture of Android or tried not to adjust it while still being able to work with CrossVM. The first question is why CrossVM? Well, there are many different levels that you can answer this question. The first is, well, we've been using CrossVM for Cuttlefish, so we should also use CrossVM on device. But that doesn't really answer why CrossVM versus other virtual machine managers. But this is developed in-house. It's in Rust, so it's very easy for us to adopt. But then there's another level to ask this question, which is why virtual machines at all? And virtual machines give us more isolation than you can get with a standard process. And they also allow us to run code that we weren't able to run before. So we definitely decided that we wanted to use CrossVM. And now I'm going to talk about some of the difficulties with using it. So CrossVM is a really large code base, and Android's a really large code base. So there are a lot of logistics just to get the code running there and working so that we can actually ship it on device. So I'm going to be talking about that first, and then I'll talk about the architectural impact of CrossVM. I put some bubbles here up of different code bases in Android just to show off kind of where CrossVM fits in. It's not really to be trifled with. Adel, the Android compiler, is 1/10 the size of CrossVM, and that's considered a pretty big code base. You can see CrossVM is almost as big as all of the hardware interfaces in Android. But when you compare it to Framework Space, the largest project in Android, it's about an order of magnitude smaller than that. So you can see it's not to be trifled with. It is a big code base, but it's also smaller than a lot of the things in Android. One of the major difficulties with using CrossVM in Android is it's released on a different schedule. So CrossVM kind of follows closely the Chrome OS release schedule, which has very rapid releases, whereas Android, as you may know, has usually a yearly dessert release. And so in order to ship it, what we do is we merge CrossVM every week from upstream. And at a certain point when we want to finalize the release, we stop the regular merges and we just take critical fixes. And so that kind of allows us to come up with a stable version of CrossVM that we're comfortable releasing in a dessert, while also taking all of the new features that are developed in CrossVM as soon as they're available. Another big difficulty, and this goes with importing almost any external project, is having separate build systems. CrossVM, like most things in Rust, use the Cargo build system and dependency management tool. And Android uses Android Soon, which is a custom build system. And so we actually have to use a tool in order to convert things over that we inherited from the standard Android Rust work. And CrossVM is actually so big that we wrote a custom tool to make this process a little bit faster. And the end result is we have the CrossVM code base, and it gets converted to a format that can be digested and used directly inside of Android. But there is one difficulty that we encountered many times with this, which is dependency management. And in a large software project that's used by many different people, when you add a dependency to the root project, all the people that depend on the project also need to depend on these dependencies. And so when CrossVM adds a dependency, it means that Chrome OS and Android and other projects need to add dependencies as well. And so because Android needs to convert dependencies into Android Soon and needs to import them as well, we've actually worked with the upstream CrossVM team in order to use this cargo.lock file and ownership on this file to track the dependencies as they're being added and try to limit the number of dependencies that we need to maintain. And finally, in order to intake such a large project, we need to have assurances that it's actually working, that there's not some issue that's occurring. And so we put up some canaries to make sure that we're aware of any major issues. And so here what you can see is our boot time dashboard of something booting inside of CrossVM. And, we have many such dashboards so that we can see when CrossVM gets updated or when other changes are made, how that impacts things. So you can see that here near the end of this dashboard, there's actually an optimization that's added into CrossVM or into the code, which makes it boot much faster. So we make sure to look at those things since we're ingesting such a large project and it changes rapidly and Android's changing rapidly, that we're able to see, oh, hey, this week there was an issue in CrossVM and it propagated into Android. And so, we need to address that, or, why did the boot speed up or why did it slow down? So we make sure to look at that. And all of those things are the steps required just to be able to use CrossVM. And it's quite a lot of things because, it's a large code base and another large code base. And, they need a lot of work to get tangled up together. But I haven't talked anything about, which is the major thing that I wanted to mention today, about how CrossVM's impacted the Android architecture. When I say impact, I mean, one thing is Android has all this code, and we don't really want Android to change significantly, right? Like as I showed on earlier slides, we have that 7.8 million lines of code in framework space. And, when you look at all that code and it's implementing a feature that an app can talk to, you don't want the app to imagine, for instance, we have a feature in the apps talking to some of this code in framework space is part of an SDK API call. And imagine we switch that API call to be implemented by a virtual machine in the future. We don't want to re-implement all that same logic again. We want to use the existing code that we have there, and we want it to work directly in the virtual machine. So when we talk about the impact on the Android architecture, we really want to keep part of the architecture the same. And the question is, how do you keep the architecture the same? How do you reuse all the code while you change all the building blocks, right? The previous building blocks of Android were processes and apps and apexes and hows and services and so on and so forth, and all the things that exist in Android. And now we've added this new piece of CrossVM, and we have these virtual machines. And some of these virtual machines might run other OSs, but a lot of them are running just a piece of Android, which I'll talk about in a second. But we want to make them feel like they were a native part of Android, like they've been a part of Android all along. And so this is kind of a short section, but I want to talk about how we did that. And we kind of did two different things. And the first is on how Android communicates with its VMs, right? I mentioned earlier that we have a piece of Android inside of a virtual machine, and we want that piece to be able to communicate with the core part of Android in the same way that the core parts of Android already communicate with each other. So here you can see on the left, we have how Android's been for years and years and years. We have, basically a single machine. We have all these processes going around. So here's process A, process B. These are things like system server, things like camera server, audio server, media extractor, init. Init doesn't use Binder, but things like hows, things like apps as well. Apps are also processes that communicate using Binder. And so we have all of these things, and they're talking over kernel Binder. And of course, if you move over to the world on the right, we have these two VMs, and they have these two processes, and they need to communicate. But because they have running two different kernels in two different VMs, they're not able to communicate over kernel Binder. And so what we did is we reinvented Binder to work over sockets, specifically in this case over VSOC. And that way we're able to use all the existing ADL interfaces, which talked over kernel Binder over RPC Binder. So all the code in process A and process B, it exists exactly as it existed before, except now underlying it, instead of the kernel Binder transaction, it's an RPC Binder. And so this is how we were able to solve this issue of keeping the architecture the same, right? The code looking the same while restructuring everything. Now that RPC Binder is used, it looks pretty much the same, except what's going on under the hood, and the security guarantees and the guarantees around memory and certain things are changed, improved. All right, so I've talked about how the communication changes, but what I haven't talked about is how we actually set up VMs and orchestrate that communication. So this is a diagram of the architecture of Android virtualization framework and how CrossVM fits into that. And so let me walk you through the diagram. So we get some sort of request. So maybe this could be from an app. It needs to do something. Maybe it's compiling an application. Maybe it's taking a photo. It could be anything, right? This diagram is not about a specific use case. It's just imagine we have some request and we have a virtual machine that implements part of the logic required to make that request happen. And so we need the virtual machine. So the request goes in. Maybe it's a request to teleport. I'd like to teleport to France. So we get this teleportation request in, and it comes into a system process, maybe teleportation manager and system server. And teleportation manager says, whoa, teleportation. We can't have that in an ordinary process. That is a very important thing. It needs to be isolated in a virtual machine. And we need to make sure everything's going right with that. And so we want to put it in this very constrained environment. The teleportation manager would say, hey, Virt manager, give me a VM. And Virt manager would say, sure. And it would fork off a CrossVM process, which would make a virtual machine by talking to, on Linux dev KVM. And it would give a handle to that virtual machine back to the originating process. So now that the virtual machine's been set up, the teleportation manager and system process can talk over RPC binder directly to the virtual machine, exactly as if it was another service in Android that it was talking to. That's the exact same ADL interfaces that you would use to talk to a process on the same device, now talking to the virtual machine. It should just work like that, except there's one more difficulty, which is that we don't want to completely rebuild a whole new operating system for every virtual machine. So what the virtualization framework team have also done is taken a piece of Android called MicroDroid and caused it to be duplicated in Android in the virtual machine. So that way we have the same code for init used in two different places, and we don't need to maintain two different versions of it. And it also makes the process inside the VM behave a lot like a regular Android process. It can expect some of the same things that you would expect in Android. So, for instance, there's no Java processes in the virtual machine, but because there's init, you are able to do things like spawn services just like you can in Android. So a lot of the code that works in Android already works in the VM as well. So as you can see, except for these additional components of Virt Manager and CrossVM that are added here, if you take those out and you erase the lines between the VM and the Android host, and you push the init boxes together, you'd have a diagram that looks exactly like the communication we have today. So that's what the secret is of making such a large software project work, is by making the stuff that already works work in the new environment. So in order to take advantage of those symmetries, we've tried to preserve all of the client code and all of the server code and how something interacts with another piece of the system, and just reinvented a new way of it doing that, so that we don't have to be concerned in all of our existing code what underlies a specific communication. All right. So thank you for listening. That's been a talk on CrossVM and how it's been ingested and changed Android. And thank you so much.
Thanks, Stephen. It's great to see how virtualization is being integrated tightly with the Android platform to provide secure and isolated computing environments. Okay, next we'll hear from Will Deacon, who will be walking through pKVM, an extension of the open source KVM hypervisor for Android. Take it away, Will.
Hello, and welcome to my talk, Extending the Open Source KVM Hypervisor for Android. I'm Will Deacon. I work in the Android systems team in London, and I'm going to talk about how we've taken the upstream KVM hypervisor, it's a mature hypervisor deployed for a number of years within Linux, and extended it for Android. And the interesting thing here is that the KVM hypervisor is a well-established mature hypervisor, part of the Linux kernel, and we're extending it so that we can deploy it in Android on your phone. So before I go into the sort of nuts and bolts of the hypervisor, I'm going to talk a bit about what we're doing here. So the thing we're working on is actually called the Android Virtualization Framework. Of course, that's also known as AVF because we have to have a 3-letter acronym for most of these things. And the AVF achieves a number of things. I've listed sort of 3 high-level things here. On the left-hand side, enables dynamic hardware-accelerated virtual machines in Android. The important part here is that by enabling dynamic virtual machines, Android doesn't need to have any knowledge of the virtual machines you want to run, for example, when you turn your phone on. So you can create, configure, spawn, manage, destroy these things completely at runtime, which is really, really flexible. There's no ingrained knowledge necessarily of the actual VM payloads in the hypervisor. And secondly, they're hardware accelerated, meaning that the CPU has extensions to support the running of virtual machines. They run relatively quickly, near native speeds. And when your VM is running, it's sort of running on the metal, if you like. So that's the one thing that AVF supports. It was launched in Android T, and it's actually shipped on the Pixel 7. So if you've got a Pixel 7, you've got Android Virtualization Framework. You can go and have a play with it. So I'll talk a little bit about that at the end with some pointers to documents you can read if you're interested. And then thirdly, on the right-hand side, the really interesting thing about AVF, and I think what sets it apart from at least traditional uses of virtualization, and specifically with KVM, is that the virtual machine environment actually provides an isolated confidential computing environment, meaning that the data in the virtual machine by default is not accessible to the rest of Android. We don't guarantee availability, so Android still decides when to run a virtual machine, when not to run it, even when to tear it down. But the data within that virtual machine remains confidential by default. And that's really important. That's kind of the big thing that we've done differently with AVF. So that's AVF. It's a bit of a whistle-stop tour because I haven't got very long, but the key part of AVF that enables this is protected KVM. So this is not 3 letters, it's 4, PKVM. It's the extension to KVM that we have implemented to enable this confidential computing. So I'm going to talk a little bit now about what that looks like and roughly how it works so that you get some idea of what we've done. So this rather daunting looking block diagram, on the left-hand side, we have user space at the top, down to OS kernel, which is where your operating system runs. And then at the bottom, we have the hypervisor. So that's the most privileged at the bottom. And these correspond to exception levels in the processor. So on the left-hand side, that dotted box that's labeled host, and that's actually, in AVF, that's your main Android. That's your Android system. You turn on your phone, it boots up Android, it's booting the host. And you have apps, you're used to apps, you've got services, you've got your Android Linux kernel running as the OS kernel. But there's a couple of things here worth looking a bit more closely at. One of them is the green box marked CrossVM. So that's actually part of the Chrome OS project, CrossVM, Chrome OS Virtual Machine Monitor, I think it stands for. And that talks to the Android Linux kernel, and specifically it talks to this thing called KVM, the KVM driver. And that's the way that the Android Linux kernel is going to talk to the hypervisor to manage virtual machines. So that red KVM box can then talk down to the hypervisor box to manage the virtual machines. So the virtual machine we have here is the dotted box on the right-hand side labeled guest. And it looks pretty similar to the host, right? We also have apps. We also have services. You can run Linux applications and to some extent Android applications. It's more of a limited environment, but more on that. We're using a trimmed down Linux kernel called the Microdroid Linux kernel. So this whole environment in the guest is actually known as Microdroid. It's a small Android designed for running small payloads in this confidential environment. And the reason we can trim down Microdroid, the Linux kernel for Microdroid, is because we don't need all the bells and whistles that Android has. So even the networking stack, we don't necessarily need all of that, for example. So we can really make quite a small payload for these VMs, meaning that it's less memory overhead and it can boot more quickly, things like that. So that's all based on Linux. We've also got U-Boot in the guest, which is used as the bootloader to boot that Microdroid. So the protected KVM is the hypervisor at the bottom. I've had to mark this as not to scale because it occurred to me that judging by this diagram, it looks like it's about 3 times the size of the Linux kernel. That's not true. It's really quite small. In fact, that hypervisor component is actually part of the Linux kernel. It peels off during boot, and I'll explain how that works later on. It's about 100 kilobytes of text. It's really not very big. And the thing it does, which is crucial to this confidential environment that we're talking about, is it installs this stage 2 translation around the host and around the guest. And I've drawn that in the corner of the relative boxes. The stage 2 translation effectively partitions up the physical memory in the system to say, hey, the host can only access these pieces of memory and the guest can only access these pieces of memory. And that's what gives you the confidentiality, because it enforces ownership and permissions for each page of memory. So what exactly is being protected? I'm going to walk through a couple of scenarios here about how this protection works. So the first one here is when the hypervisor detects an access violation. And I'm going to go through this step by step, but imagine we have a protected virtual machine. PVM is your three-letter acronym for that. And it asks Android for some memory, because Android is dishing out the memory, for the physical memory in the system. So the PVM says to Android, hey, I'd like some memory, please. Android donates this memory to the PVM. Now, this transition for the memory means that the memory is now owned by the PVM and becomes inaccessible to Android. So no longer accessible to Android, becomes read and writable by the PVM. But let's say that an Android attacker now attempts to access the memory, and you can tell this Android attacker on the right-hand side is evil because he's got these glaring red eyes. He's going to try and access that memory that is just donated to the PVM. And the hypervisor will detect the access violation, prevent the access going ahead, and slap it on the wrist. And I'll talk about how that works. Interestingly, the same mechanism here is also what protects Android from the PVM. So it's mutual distrust. The stage 2 translation, which is used to control this ownership, isolates the guest from the host, i.e. the PVM from Android, but also Android from the PVM. So here we go, step 1. I just walked through it. Let's go through it step by step. So here's the PVM on the right-hand side. It says, hi, Android, please can I have some memory? And that message goes via the hypervisor back to Android. Android says, sure, here are 4 kilobytes just for you. And you can see this 4 kilobyte page being transferred over to the PVM. And this is not a copy. This is really a change of ownership for that physical page. The PVM is, wow, so generous, because it's 4 kilobytes. For some reason, that's still the page size, even though it was sort of originates from the 60s, but hey, that's where we are. The PKVM hypervisor, during this transition, goes and updates the stage 2 page tables on the left-hand side, the bottom left. So crucially, it's going to actually update 2 stage 2 page tables there. It's going to update Android stage 2 page tables to say you no longer have access to the page, and it's going to update the PVM stage 2 page tables to say you now have access to the page. So they're the updates that the hypervisor is going to do, along with some security checks to make sure that that's a legitimate transition. And now the attacker comes into play. We've got the page. You can see that it's inside the PVM down at the bottom, because it's only accessible by the PVM. It's owned, and actually the PVM has mutated the data so that those ones and zeros have changed a bit. It's got some secret information in there. I think it's actually the ASCII for cat. So Android wants to read that secret data. It says, "Mwahaha, only joking. Now I'm going to read your secrets." And it tries to read it, but PKVM swoops in and saves the day. So the CPU will actually perform a permission check using those stage 2 page tables. They were updated by the hypervisors to say Android can't access this page. So we'll get an access violation exception to the hypervisor, which will then inject a fault into Android saying, stop that right now. And if it was an access on behalf of an application, that application will be terminated. And crucially, that secret data of cat in the PVM page, Android never managed to read what that was, and PVM's data has not been compromised. So we sort of give an integrity guarantee there. So that's all well and good. We've got this confidential computing environment. We've got mutually distrusting entities. We've got the hypervisor making sure that they can't access each other's memory. But by default, the PVM's memory is none of it's accessible to Android. You can't do a lot with that because you can't get anything into it. So you can't perform any I/O. So you can't do anything interesting. It's kind of just running in its own little world that you can't actually interact with. So PKVM provides a mechanism for sharing memory. And this is always initiated by the PVM. So the PVM can choose to share memory back with Android for things like I/O. So in this situation we're going to walk through now, the PVM shares memory with Android. The hypervisor makes the memory accessible to Android. Still owned by the PVM, but it goes into this sort of shared state. And then there's some communication that happens. So same kind of deal. PVM talks to the Android, says, hi again, Android, let's use this memory together. And it's got some information in there. I think it says dog instead of cat this time. So the hypervisor says, all right, fine, you're very cheerful. And sorry, not the hypervisor, Android says that. The hypervisor is going to go and update the stage 2 page table. So now what we do is we update Android's page table to say you can access this page. So both the PVM and Android have read and write access to this page. But we also update the PVM's page table just with some software metabits to say this has been shared with someone. It doesn't affect the permissions. It's just so the hypervisor can track that it's actually been shared with Android. So now you can see that this page is really accessible by both Android and the PVM, and they can use it for shared memory and to bootstrap I/O. And in this case, it says dog, so they're woofing and barking together, and that's your shared memory communication. So that's like the high-level protocol of what we've enabled, the kind of things you can do between Android and these VMs, the confidential environment we provide, and how you can share memory back selectively to perform I/O. How do we do it? Well, it's quite clever, actually. This is interesting. So you could ask, is it a kernel? Is it a hypervisor? Well, yes, it's Linux. All of this is part of Linux. So even in that initial diagram I had, which had the hypervisor right at the bottom, with the way it's deployed, it's all deployed as part of the same Linux kernel image. So when you turn on your phone, Android Verified Boot loads this generic Linux kernel, and that's packaged along with the PKVM hypervisor. In fact, the PKVM hypervisor source code it lives in the Linux source tree. So you build your image and it contains the hypervisor. And the new thing we've added for PKVM is during boot, the kernel deprivileges itself. And you can see that as the sort of second column in this diagram. So we start off with the Linux kernel and the hypervisor together, and then they split. So you have the generic Linux kernel running on top now of the protected KVM. And that deprivilege step coincides with protected KVM installing that stage 2, sort of activating that stage 2 translation table for the Linux kernel. And then after that, the kernel can proceed to do all the things it would normally do. In this case, there's no guests, so pretty much all of the physical memory is going to be owned by the kernel, by Android, with the exception of the small amount of memory that's needed by protected KVM, for example, to map its small 100 kilobytes of text. And that just stops the kernel being able to modify the hypervisor to subvert it. So within the hypervisor, we track every 4 kilobytes of physical memory using using the page table, using this structure. This is the sort of high-level state machine that we have. So you've got an 8 gigabyte phone. Every 4 kilobytes can be in a different state. It could be owned. If it's owned, you've got exclusive access to it. So if it's owned by Android, it's got exclusive access to it. It can share it with other people. It can read, write, execute it, all of that kind of stuff. If you share it with someone, as we saw earlier on when the PVM shared a page back with Android, it becomes shared owned by the owner. So in the PVM stage 2, it becomes shared owned, and shared borrowed in the target. So it becomes shared borrowed in the in Android, in the host. And in that case, it would transition from no page, which means there was nothing there because it was inaccessible, to shared borrowed. So this is roughly just how we track these, every page in memory with a couple of bits. So I think this whole day is supposed to be about open source. And I think all of the components of the Android virtualization framework are open source components, which is really lovely to work with. And normally when people talk about open source software, particularly with Linux and the Linux kernel, they say, oh, we're standing on the shoulders of giants. But in this case, it's a bit funny because we're sort of building under the feet of giants. We're going underneath. We've got a small reactive hypervisor layer that relies on Linux and KVM. It supports the whole thing. And it's very powerful because PKVM, like KVM, is tightly integrated with the Linux kernel, and it's shipped as part of the Linux kernel image, the GKI binary for Android's case. And that means that the hypervisor can actually use data structures, code, algorithms from the Linux kernel directly. There's nothing to stop it. And there's no sort of stable ABI that you have to maintain. You don't have to worry, for example, about running next week's hypervisor with last year's Linux kernel because it's all part of the same thing. You update the source code, you just update them both at the same time. And that's very powerful. It means that the kernel can handle an awful lot of things for your virtual machine. It can handle scheduling, it can handle device drivers, it can handle power management. And Linux is quite good at that. So it's nice that we don't have to have that in the hypervisor. It means the hypervisor layer stays very small, it stays very simple. It's inherently portable because it needs very little knowledge of the underlying hardware. There's a little bit for IMMUs, but by and large, it doesn't need to know anything about the underlying hardware. So we're really leveraging the existing open source KVM and Linux kernel implementation to enable this hypervisor and keeping it small. So what do we want to work on next? Well, like I said, we've been using open source software, but we're not just consuming it. We're actively upstreaming our efforts, and we're not waiting till we're done before we start doing that. So we're actively upstreaming. We've already landed a load of stuff in 6.1, and we're in the Linux kernel, and we're continuing to upstream. We've also upstreamed various things into U-Boot and other open source projects, including AOSP. One of the really interesting things is we're not the only people doing this, right? Confidential computing is quite popular. And there are other solutions which look somewhat different in terms of implementation to what we're doing with PKVM and AVF, but which rely on hardware extensions. So AMD have SEV, Intel have got TDX, ARM have got CCA, and that's all well and good. They've got their own back-end implementations. But when it comes to core code in the Linux kernel, shared code, it's in everyone's interest not to duplicate the core logic. It's easier to maintain, easier to reason about, easier to program for. So we're involved in those discussions as well to make sure that it works for everybody. And we have development trees tracking the mainline kernel releases. So it's not just that we've shipped only in the Android kernels. We're keeping track of all the release candidates upstream and upstreaming as we go. I think one good example of one of those upstream core discussions actually is this thing called Guest Private Memory. So there's a Linux Weekly News article here. It's very good. Go and have a look. The crux of the problem here is that when you donate memory to a PVM, as we saw in that first example, the PVM says, hey, I want 4K. Android gives it 4K of memory. Android can no longer access that. The host kernel, Linux, can no longer access that 4 kilobytes of memory. And Linux isn't really used to that. It's not used to saying this random 4K of memory is now inaccessible. If you access it, you're probably going to kill the system. It's going to have to reboot. Furthermore, we need a way of talking about this kind of memory. We need to be able to talk to user space about memory that is not accessible. So this is challenging, and there's nothing PKVM specific or anything else specific to this. It's just the nature of confidential computing. So we've been working together with the kernel community to develop user ABIs and a proposal that's suitable for everybody. Right now in Android, we've had to do something in the interest of time, but once upstream align on a solution, we will switch Android over to use that. But it's just a good example, I think, of a common problem being solved by different backend implementers. So with that, thank you very much. I hope that was interesting. If you want to get in touch with the team, we have an email alias. It's quite busy, but you can shoot questions there. We have a Git repository with lots of different trees. If you just want a deeper dive, I've deliberately kept this quite light so that you can get a feel for what we're doing. If you want to go into the technical details, there's a deep dive talk from KVM Forum from my colleague Quentin Perret. That's the YouTube video there. That's great. It's about an hour, maybe a little bit longer, of quite technical material on the hypervisor itself. Alternatively, if you're interested in actually interacting with MicroDroid and trying to spin up a virtual machine, perhaps on your Pixel 7, the documentation at the bottom should help you with that. So with that, thank you very much, and I hope that was enjoyable.
Thanks, Will. PKVM is the backbone of Android virtualization framework. Building on top of Linux and KVM means we have the flexibility to bring existing KVM-based virtual machines to Android in future. Next up, Alistair Delva will be discussing Cloud Android and updates on the Cuttlefish virtual device. Over to you, Alistair.
Hi there, my name's Alistair Delva. I'm a software engineer working on a product called Cloud Android. Today I want to share some details about awesome new features in the Cuttlefish reference device. And everything I'm talking about today is available for you to download in AOSP. So what is Cuttlefish? Last year I presented Cuttlefish for the first time, and that presentation is still available on YouTube if you want to take a look. For the benefit of those that haven't seen it, I'm going to explain what Cuttlefish is and how you might want to use it in AOSP. So what is Cuttlefish? Cuttlefish is a device port of Android optimized for virtualization. What that means is that we've taken all of the things in a physical device that you need to build a useful physical device. We've tried to provide analogs for those features in our virtual platform. Things like camera, touchscreen, display, GPU, they're all being virtualized. And we've tried to do that in a way that is optimized for performance and optimized for the available feature set, so that the feature set in the virtual device as closely as possible matches what's done in the physical world. and that means that we get pretty good performance, pretty good correctness, and alignment with physical devices. The project as well also provides tooling for local and cloud execution. So when you build locally, there's a tool that gets produced by the build called Launch CVD, and that tool will immediately start the virtual device on your machine, assuming you've started you've gone through the setup procedure. But we also make it possible to, from that same build environment, to launch the virtual device on Google Cloud. If you have a Google Cloud account set up already, you can actually start the virtual device, either a local build that you've done or some pre-existing build from ci.android.com on Google Cloud, and it will download the build onto Google Cloud or upload it from your machine, and then it will start the same local launching procedure, launch CVD, to start the virtual device. One of the goals of Cuttlefish and AOSP is to provide a scalable, reliable, and conformant device. Scalable meaning that we can take advantage of the compute power available on the machine that it's running on, albeit on a small workstation or development board, or a large server with many CPUs and a lot of RAM. And part of the way that we achieve that scalability is by allowing multiple instances of the same Android device to run on the same machine at the same time. So in the diagram, you can see on the right-hand side, we have the Linux host, which is the machine you're running Cuttlefish on. The VMM is the virtual machine manager. That's the virtual platform, essentially. It's providing the features of the Android virtual device. And then underneath that, we can have many of these Cuttlefish guests, which include a whole operating system kernel and Android user space. And the user space builds can be the same. They usually would be the same if you were running like multiple instances of Android for sharding CTS or something like that. Or they might be multiple different guest images if you were running, say, an Android 10 version of the phone against maybe an Android 13 version of a foldable device. You'd be able to run them both at the same time on different versions. So we take advantage of this scalability, reliability, and its conformance characteristics, its correctness and conformance characteristics in our scalable CI system. And Cuttlefish is deployed and has been deployed for a long time now to the Android AOSP continuous integration system. So when you upload a change to AOSP and maybe a Googler sees your change and starts what we call pre-submits on that change, that will most likely be run through the Cuttlefish virtual device to validate that your change is correct. So we trust the system enough, the virtual device enough, to use it in our own continuous integration system. So here's an example of actually grabbing the source, building it, and running it locally on your workstation. Now, the first step, and this was contained mostly in my slides from last year, but this is just a condensed recap for you. You can go to source.android.com/doc/setup/create/cuttlefish, and it will actually outline all the steps to install the Cuttlefish dependencies and configure a system for running Cuttlefish for the first time. You do need to always follow those steps at least once on any machine that you're going to be running Cuttlefish on. Once you've run those steps, though, you can get a copy of AOSP. So the example here actually includes the cloning and building instructions for AOSP as well. Once you've cloned down the platform, which is that make dir repo init and source command, you can then launch the special Cuttlefish targets. In this case, I've launched AOSP CF x86-64 phone user debug. But if you want to do an ARM64 build instead of an x86-64 build, you can also do that. Last time I discussed this topic, ARM64 was more experimental last year. But now we consider it to be kind of production worthy. So you can also just use that AOSP-CF ARM64 phone user debug if you want to build an ARM64 version of the Cuttlefish reference virtual device. It will run more slowly on an x86-64 machine because when you run that launch CVD command there at the end, it will be using a virtual, like an emulator to emulate ARM64. But you can also take that build that you've built on your machine and you can copy it to an ARM64 device, like a dev board or a server. And you can actually run the virtual device implementation on those platforms at full speed. It will run using the virtualization capability of ARM64. So both of these options are viable in AOSP. Or if you don't want to build and run Android locally on your machine, maybe you have a machine with lower specification, or you want to run a more complicated Android environment for some reason, or you just don't want to build it because it does take a long time to build. You can still use artifacts from AOSP to experiment with the virtual device. So in the case here, we're using the acloud command, which is part of the AOSP environment. When you clone down this code and you run launch a target, you'll get acloud in your path. Or you can download acloud from another location just to have the acloud pre-built. And then you can run the acloud create command to create a virtual device. This will use any pre-existing Google Cloud credentials that you may have on your machine. And it will create a project in AOSP. It will download the build that you specify from ci.android.com, and then it will run the virtual device and allow you to access it from your web browser. So the example I've given here, there's two possible ways of doing it. You can use the acloud create with no build ID, and it will just fetch the last known good build from ci.android.com. Or if you want to fetch a build from ci.android.com and run it locally, you can do that as well. So this isn't using acloud. This would be using Launch CVD. You can go to ci.android.com. You can look at the builds that are available, click on the AOSP_CF targets, and then download two files. It's either the .img.zip file and the CVD host package file. You need both of those files. Download those and extract them, and you'll be able to run that Launch CVD tool to actually run that pre-built Android virtual device. So one of the new things I want to talk about this year is the fact that we've really invested in exposing every form factor of Android that's available in AOSP through the Cuttlefish virtual device. So we have example implementations, not just of the phone target that I've mentioned already, but also of a foldable device. So I'll talk more about that in a moment. The Android automotive device, Android TV, and the Android Go targets as well. So these are all supported in AOSP. You just have to vary the name of that launch target when you launch. So you can use AOSP CFX8664 foldable, for example, and it will build a foldable device instead of a phone device for you from AOSP. And as more variants of Android are become better integrated with AOSP, we'll continue to expose those using Cuttlefish. So two of the main areas of expansion and new form factor support are the foldable experience and the automotive experience. The foldable experience in AOSP, as I mentioned, you can use this AOSP CFX8664 foldable user debug target to set up your launch environment to start your build process. And then one of the main differences you'll see when you access the user interface on Cuttlefish, which is based on WebRTC and can be accessed through your local host machine, :8443. The port is 8443 for the WebRTC interface, is that you'll see these new buttons, these blue buttons that you can see in this GIF on the left-hand side. And these are actually changing the different foldable configurations of the device. So you can, for example, you can put it into vertical or horizontal orientation. You can have the hinge fold vertically or horizontally. So, for example, like clamshell, laptop style, or you can do it like a more conventional foldable device, and it will actually show you the multiple displays for the foldable device. So, as you can see, and when that fold transition happened there in the GIF, the second display will show up, and you can interact with the device through that second panel. And so this is one of the main differences between the phone device and the foldable device, is giving you these buttons to perform these interactions. So this is just giving you an opportunity in AOSP to explore with kind of the latest and greatest UX features of Android, and also hopefully makes it easier for you to experiment with building your own foldable device. We've picked a target for the foldable device, which is, we believe, representative in terms of screen size and hinge location, but all of the meta files that are used to produce this configuration are in AOSP and are customizable. So if you want to go into those files and change the hinge location or the sensitivity of the hinge or the point at which the transition starts for your hinge, or the screen sizes of your different displays, that's all something you can change in AOSP, and it will be reflected immediately in the Cuttlefish virtual device when you use the foldable target. So definitely something to check out. The second big thing, which is focused really on the automotive experience, is Cuttlefish's multi-display capability. So when you run with the AOSP CFX8664 auto user debug target, the target will start up with a WebRTC interface that contains two pre-configured displays. So you'll have the driver heads-up display, which is the display you can see in this image on the right-hand side, and you'll also have the infotainment display, which is where the maps are being shown currently on the main panel. As you can see, I'm running Google Maps right here, and we simulate the GPS location capabilities, so we can actually set routes and test all of that mapping capability on the virtual device as well. Multi-display is not specific to automotive. It's the first platform that we've exposed it on because it's typical for an Android Auto embedded device to have multiple displays. But the multi-display feature can also be used with other Android configurations. We do expose that capability in AOSP. But by default, when you launch this automotive target and you run it, it will pre-configure it with two displays, the heads-up display and the infotainment display, and it will allow the user to interact with both of those displays. These are being delivered as two separate video streams through WebRTC to the web browser, and we're using sort of like iframing to handle these two displays in the main system. And you can see in the automotive model here that we don't have multiple sets of buttons because the interaction buttons for controlling things like the volume, the home button, etc., are global shortcuts for the device. They're not per display. So when we talk about the other major thing that we've done in AOSP for Cloud Android for Cuttlefish is it's adding the multi-virtual device capability. So this is something that's very important for exploring device-to-device interactions. And one of the ideas, one of the motivations for this feature was that we really want to make all of those device interactions in the Android ecosystem work together better. So the Android Better Together initiative is all about making sure that Android and other Google devices can interoperate with each other and you have a good experience as a user and transitioning from one device to another. And any cases where those devices are working together to perform a task, we want to make sure that those experiences are good and they're reliable. So one of the things that we've done is we've made the virtual device also support having these multiple virtual devices running side by side. And allowing these virtual devices use cases to be explored using the virtual device. So we can even look at device-to-device interactions which perhaps don't even exist yet, such as form factors which don't exist, or application use cases that don't exist yet. And we can explore those by building out virtual devices that use those different device models and have them connected together. So one of the ways of how we're doing that type of connection is we've really invested in adding the better Wi-Fi and Bluetooth simulation, so better network connectivity between the different devices. So in AOSP now, the previous Cuttlefish networking stack has been removed. This provided a single ViRT Wi-Fi access point, but it didn't allow any of the things like Wi-Fi encryption or Wi-Fi protocols to be specified. And it would only allow you access to the internet. It was like a fake Wi-Fi network. The new implementation creates another VM which runs the OpenWRT project, which is an open source Wi-Fi router project. That project is running in a separate VM. We call it the Access Point VM, and is connected together over the network with the other Android virtual devices. So the OpenWRT has now assumed responsibility for the Wi-Fi credentialing and other capabilities on Wi-Fi. And the virtual devices can be linked together using those Wi-Fi interactions. Root Canal, which had been mentioned in previous years, but that's our virtual Bluetooth implementation, and that's also been modified to support multiple virtual machines connecting to it at the same time. So devices can see and pair with each other. File sharing between VMs is now possible using Nearby Share over Wi-Fi and Bluetooth connections. And a stable implementation of this will be due in the first half of 2023, but the code is available now in AOSP, and the structure shown in this diagram is currently how it works in AOSP. So really, that's all I wanted to cover. This is, as I mentioned at the start, that we're a fully open source project. Everything we do is in AOSP and made available in AOSP. Setting your device up is documented on source.android.com at that URL. And of course, AOSP contributions are always welcome. So please take a look at Device Google Cuttlefish and the Android Google Source project. And if you do upload a change, somebody on our team will take a look, and hopefully your change can be merged into the project. So thank you.
Thanks, Alistair. Cuttlefish is already an indispensable tool for our internal testing and development of kernel and virtualization features. And as Alistair described, it is now also a platform for running other virtualized form factors and multi-device use cases. As a reminder, all the content will be available on demand after the event and published on the Google Open Source YouTube channel next week. The content will also be available with captions in English, Spanish, Chinese Mandarin, and Brazilian Portuguese. To access captions, click on the setting icons located at the bottom right-hand side of the video player and select Subtitles/CC. You can then scroll to select your desired language.
Okay, friends, that's a wrap. You all know what it means. It's time to join us for the after party by clicking the Watch Live button on the event's agenda page. Today's speakers will also be joining us, both for some Q&A, and we'll also have an exciting quiz ready for you. We hope to see you all there. Thank you.